is the x range from 48x, okay, up to 96 inches, right? So what we have now is we have P over 2, and you have P over here, and we are aware that the distance from here to here is 48, and this is our distance x, and the distance from here to here is x minus 48. Okay, because x is greater, so that's why it's x minus 48. So again, positive bending moment assumption. And then when we do our static analysis, so we are now going to do our, we're going to take our moment at the red dot now, as you can see. Okay, we're going to take the moment at our red dot. So this will be summation about moment about z, the function of x is equal to 0. So you have p over 2 is going in a clockwise direction, so minus px over 2, right? And then the other one is going in an anti-clockwise direction, plus by p multiplied by x minus by 48. Okay, because the distance is towards the red dot, that's why it's x minus 48. Okay, and then plus by m as a function of x, this is equal to 0. So when you get this, you will expand the term minus px over 2 plus by px minus by 48 p plus by m as a function of x, the whole thing will be 0. So this will be equal to positive px over 2 minus by 48p plus by m as a function of x is equal to 0. So m as a function of x is equal to minus px over 2 plus by 48p. So when we substitute x is equal to 48, right? If we substitute x is equal to 48 into equation 2, m at 48, this will be equal to minus 24p plus by 48p, which is also equal to 24p, which is also at the same point. Okay, so this is correct. So when we substitute, I think you can see the answer. When we substitute x is equal to 96 inches, right, into equation 2, we have m as a function of x is equal to minus 48p plus by 48p. The answer is equal to 0. Okay, so this answer is over here. And we know that if we look at the parent function, the slope over here, right, because it's a function of x, this is a gradient. It is what? Negative. So the line is coming down in a negative way. Okay. So from here, right? So just to quickly recall bending moment diagram for all of you that cannot, or those of you that cannot remember, sometime I cannot remember also. So just to quickly, so we know that mx occur at 48 inch, and the moment max is equal to 24p. Okay, so by going back to this diagram, right? So the equation we're going to use is stress allowable is equal to mx multiplied by y over IZZ. Okay. So MX, the allowable is what? The allowable is I think it is. Can't remember. Sorry, 8,000. Okay. So 8 times 10 to the power 3. Mx is equal to 24p. The y value shows the furthest distance away from the centroid. Okay, so it's 5 plus 2 plus 2 is 9. Divided by IZZ. IZZ is, I think is, let me have a quick look. I think it's 2902. Let me have a quick, yep, 2902. So therefore P will be equal to 8 power 3 times 2902 times by, or not, times divided by 9 divided by 24 is 107.481 times 10 to the power 3 pound force. So it is the highest, okay? And it's what we expect, isn't it? Right? Structures can take normal stresses better than shearing stress. Okay. That is very typical of wood. Okay. So for most ductile material, I'm going to assume that wood is ductile. Okay. It's only brittle material that can take compression very well, cannot take shear and tensile. Okay. So from here, we know that the P allowable, so the P allowable, okay, for mode 1, fastener P is equal to we calculated earlier 6910. Then we have mode 2, shear stress due to wood. P is equal to 80 and 83.511 times 10 to the power 3. And finally, mode 3, normal stress due to wood. P is equal to 107.481 times 10 to the power 3 pound force. So over here, finally, you have to pick the lowest or select the lowest. So P is equal to 6910 pound force. Okay. You pick any higher than that, the fastener will fail. When the fastener fail, does not matter the shear stress due to the wood or the normal stress due to the wood. Okay. So as I say, this is and if you go to the engineering world, okay, this is a very typical problem. And this is also part of our course. So after your term test, you'll learn Mohs circle. Then learn Mohs circle, we learn combined loading. And we're going to do more of this. Okay, so much more of this. That's why if you look at a question like this, it combines 3 subtopics, right? You have fastener, you have to understand fastener, longitudinal shear, you have to understand thin wall and non-thin wall shearing stress, and you have to also apply normal stress due to bending moment, and sometimes also a combine of normal stress due to axial load and bending moment. Okay, right. So this is a very extensive example. Okay, so the next, I think I'm going to go through at least the next 2 examples, and the next 2 examples are very it's not confusing, but it's the first time you have seen it. It can seem a little bit overwhelming, but as long as you apply the rules that I teach you, you will be fine. Okay, let's look at the next two. Before I carry on in the next two examples, anyone, any questions so far regarding this problem? Okay, I don't hear anything. So let's look at the next example. So as I said, the next example is not necessarily difficult. It's just you have to apply what I teach you and you'll be fine. Okay. And when the first time when I saw this structure, I also panicked. Okay, to be frank. Okay, let's look at this example. No, number 2. So the beam is fabricated from two equivalent structure T's, okay, structure T's and two plates. Okay, so they call this T's because it's as a shape of T, and these are our plates. Okay, that is our that's our plates. And what they mention is each plate has a height of 6 inches. Okay, so the overall height is 6 inch and a thickness of 0.5 inches for the plates. If a shear of V is 50 kilopound force is applied to the cross section, determine the spacing of the bolts. Okay, we have to determine the spacing of the bolts, and each bolt can resist a shear force of 15 kilopound load. Okay, so we are given that V is equal to 50 times 10 to the power 3, okay, pounds. And we are going to determine S, okay, where the resistance force or resistance fastener force is at 15 times 10 to the power 3 pounds. Okay, so if we were to look at this structure now, right? So over here, if I'm going to go draw the cross-sectional view, before I draw the cross-sectional view, I'm going to label this as my X. This is my Y. And over here, this is my Z. So if I'm going to sketch the cross-sectional view, so Y is Z, and this is our rotation of X, right? So you have a T, right? And then you have two plates. I'm only going to sketch up to you the geometric centroid. Okay, so I'm going to declare that over here, this is my geometric centroid. Then we have a fastener put over here. Okay, so this is our fastener. Okay, and we realize that over here, why I draw this, we have what? We have a double shear configuration. Right, over here, double shear configuration. Okay, so we know that the fastener is under